finish the Unijunction transistor, then I will explain the the energy level diagram required for the tunnel diodes. Okay. So coming to the Unijunction transistor, we also call it as short form as a UJT. The term Unijunction refers to the fact that the UJT has a single PN junction. So this is the representation. I mean, the reason why we call it Unijunction transistor, because we form a single junctions in this kind of transistor. Whereas if you take the normal transistor, you will come across two PN junctions, right? One junction, one semiconductor will be the emitter, other one will be the gate, and then the collector region will be there. So between each across these three semiconductors, we come across two junctions. However, in unijunction transistors, only a single junction will form. So that's why it is called a uni. Uni means only single junction. So therefore, it refers as a UJT. The UJT is useful in certain oscillator applications. We know there are different oscillators, Colbit oscillator, Wien bridge oscillator, and so on. So where these oscillator applications, these UJTs are mainly used, and also as a triggering device in thyristor circuits. So in the thyristor based circuits, these UJT acts as a triggering devices. Basically, in thyristor they use this for triggering the circuits, thyristor based circuits. These are the main application of UJT. So the UJT is a three-terminal device whose basic construction is shown in this figure. So this is the, you might have studied in your UG also. The UJT, the construction is this. We have a three-terminal. However, only one junction we come across between this N-type semiconductor and P-type semiconductors. So this is the base region, and this is base 1 and base 2. This is basically the substrate, N-type substrate. We just dope it, with the P-type material inside. Basically, we take the intrinsic semiconductor first, dope with the N-type material, and some portions we dope it with the P-type materials or P-type impurities. In the region where we want the N-type material, we just dope it with the N-type impurity. That's how basically the these type of junctions are constructed, or the devices are constructed. So due to which, what happens, we get two bases, base 1 and base 2, and the emitter. This is the emitter region, which we make the contacts, metal contacts. Similarly, here also metal contacts, and the connecting wires or terminals. These are the connecting wires. Similarly, here metal contacts, and then connecting wires or terminals. So between this N-type semiconductor and this P-type semiconductor, we just form this kind of the junction, right? So this is the junction region between this N-type material and P-type material. So that's about the construction. The schematic symbol is this for the UJT. So we have this kind of representation, a symbol for the UJT. Notice the terminals are labeled emitter, base 1 and base 2. Don't confuse this symbol with the that of the JFET. The difference is that the arrow is at the angle for the UJT. So this the UJT representation and the JFET representation of the symbols are almost similar. You just have to look at the slight deviating angles when you represent the emitter, the regions or terminals. So that's what it means. And then whereas if you take any transistors, we just call it, we have the gate terminal, the emitter, gate, and the collector terminal. Here, instead of having these type of three regions, we have a two base and only one emitter. So these are also the main thing which we have to notice and we have to remember. And then okay, so the UJT has only one PN junction, and therefore the characteristics of this device are different from those of the either BJT or the FET. Even though it is called as a transistor, the typical characteristics exhibited by UJT is different from BJT and the FET devices, because it has only single junction, PN junction, whereas the BJT and FET will have two junctions. Therefore, the current voltage characteristics, dynamic, are the any capacitance characteristics, or capacitance frequency, or capacitance voltage, capacitance frequency or capacitance voltage, all these characteristics will be slightly different from the BJT or FET characteristics. So this is the equivalent circuit for the UJT. So the equivalent circuit for UJT is shown in figure A. This is the equivalent circuit. So we have the two base region, right? Base 1 and base 2. This is the emitter region where we have the one diode PN junction is forming. This will aid in the understanding of basic operation. The diode shown in figure 4a represents the p-n junction, and RB1 represents the internal dynamic resistance of the silicon bar between the emitter and the base. Similarly, so we know that this is our the device. We are forming one p-n junction. Basically, this is a p-n junction diode, right? So one p-n junction we are forming here, and this is the basic semiconducting bar or the substrate. So substrate, right? So when only device which we forming is this p-n junction diode, one p-n junction, which is acting as a emitter, and this is how you represent this region will be the anode and this will be cathode. So between these diodes are connected between the base 1 and base 2 terminals. So it connects between these, and so when the B1 wants to, I mean when B1 is want to connect with this, I mean B2 go to the B2, there is a resistance associated with these n-type semiconducting materials that we represent as R prime B1. So base 1, the corresponding resistance, the internal dynamical resistance of the silicon bar. Similarly, there will be one resistance. So we have to separate this resistance. If it is not connecting here, we can just take only one resistance. However, this is connecting between these two regions, right? Therefore, we need to separate these two resistance between this terminal to this terminal. What is the resistance? Similarly, this terminal to this terminal, what is the distance? I mean the resistance. Therefore, we just come across two resistance. Similarly, between the base 1 and emitter terminal, the cathode emitter terminals. Um, we have the another dynamical the resistance or internal resistance, that is R prime B2, because this is between the B2 and the emitter terminal. This is B1 and emitter terminal. So this is how you have to construct the the equivalent circuit for any other the electronic devices. So when you take the total resistance, that will be R prime BB. So that means the base resistance, right? So base resistance between between B1 and B2. This is the total the base resistance or the internal dynamic resistance between the base 1 and base 2. So this is the circuit UJT circuits to for operation. I mean to measure your current voltage characteristics. Or B2 represents the dynamical resistance between the emitter and the base 2 terminals. The total resistance between the base terminal is sum of R prime B1 and R prime B2, and is called the inter-base resistance. Internal or inter-base resistance, we can say R prime BB will be the sum of R prime B1 and plus basically sum of R prime B1 and R prime B2. This will give us the inter-base resistance RBB. R prime BB. So the value of R prime B1 varies inversely with the emitter current, i.e. therefore it is shown as the variable resistor. So this RB1 resistance, the value of RB1 resistance varies inversely with the emitter current, right? So that means if you apply the current to the emitter, if you supply the current to the emitter, the resistance of RB1, right? So basically this resistance, uh, RB1 is this, right? So this is the circuit which we constructed. Basically, we just connected the power supply to this the UJT, the negative terminal to the base 1 and positive terminal of the power supply to the base 2. So in this sense, what happens? Let us assume this is a fixed one and it's a variable one. So because we are injecting the current or the electrons to this terminal, and the corresponding the variation eta into VB is this. We will come measure across this. So what happens in this case? If you apply the current to the emitter terminal, this resistance value decreases. That's what it means. Inversely related means as you increase the current in base terminal, the resistance R prime B1, the R, or the base resistance, base 1 resistance is decreasing, and therefore it is shown as a variable resistor. Yeah. Therefore, whenever the resistance varies corresponding according to the given current, we can just use it for the variable resistor. That's it. Very simple. So that should vary only in linear way. That's all. If you wanted to apply for any applications. So this is this is similar to any applications where the like sensors and all the resistance variation or any variation for a given input should be linearly varying. So that kind of systems or that kind of mechanisms can be applied for the constructing any devices. So depending on IE, the value of RB can vary from several hundred ohms down to tens of ohms. So basically several hundred ohms. That means from the ohms to kilo ohms range it can vary. Several hundred ohms. 100, okay, 1,800 ohms means basically the resistance value of RB1 can be tuned from like say 0 to or 1 ohm to the maybe several kilo ohms, 1 ohms to kilo ohms. I mean kilo ohms order can be varied. It's basically the huge amount. Again, this resistance variation can be modulated based on the doping of this n-type semiconductor and p-type semiconductor that we have discussed in some other topics in the previous discussions. Um, then the internal resistance RB1 and RB2 form a voltage divider between the divider when the device is biased, as shown in the figure B. So the internal resistance, we know the resistance across emitter and base 1 and resistance across emitter and base 2 form a voltage divider when the device is biased. So that's what when you bias a device, it basically acts as a voltage divider, basically between this and these two regions or the terminal regions. It acts as a voltage divider. The voltage across the resistance can be expressed as this. So so if you want to measure the voltage across any across any resistance, either the R prime B1 or R prime B2, we can use this relation, so that the voltage across this resistance can be, that is V R prime B1, basically the resistance across the first resistor, which is between the emitter terminal and in the base 1 terminal R prime B1. Voltage across this terminal will be basically R prime B1 divided by R prime BB. That means the resistance across the resistance across the across the resistor 1, which forms between the base 1 and the emitter terminal, divided by the total resistance, which are which is basically the combination of R prime B1 plus R prime B2, that resistance, basically the total resistance, interband resistance, and that will be multiplied with BBB, the total the power supply which we are given to this emitter, I mean to the UJT UJT to operate, that BBB, the power supply what we given. If you multiply with that, you will get the voltage drop across, or the voltage across the first resistance R prime B1. Similarly, we can calculate the resistance across the R prime B2. The voltage across R prime B2 will be equal to R prime B2 divided by R prime BB into the power supply what we the voltage what we the potential what we supply to the UJT device. This is the stand-up ratios. Another two slides. Okay. The stand-up ratios. The ratio of between the R prime B1 to the R prime BB is a UJT characteristics called the intrinsic stand-up ratios, and is designed and is designated by eta. That's eta, the Greek symbol, we know that. So this is the intrinsic stand-up ratios. That is this is how you can just measure or calculate the intrinsic stand-up ratios. Basically, R prime B1, the resistance across the base 1 and the emitter terminal, that resistance divided by the total resistance associated with the UJT R prime BB, the interband resistance. So yeah, so the interbase resistance, not interband, interbase resistance. Interbase basically means we have a base, right? So this there are two bases, one and these two. So the resistance between these two bases, we call it as the interbase resistance, right? So therefore that's how the name comes. So if you do that divided by that interbase resistance, you will get the intrinsic stand-up ratio or the stand-up ratios. As long as uh, as long as the applied emitter voltage VEB1 is less than V R prime B1 plus VPN, there is no emitter current because the PN junction is not forward biased. Because of this reason, so what happens? The voltage what we supply to the emitter base 1 is less than this value. The resistance associated with this the R calculated between the base 1 and the emitter terminal voltage plus VPN. So the diode will have its own threshold voltage. That the combination of this will give us some total voltage that needs to be given to switch on this emitter or to operate this UJT, right? So we know that there is some threshold voltage all this for this any electronic devices. Similarly, the BJT has a threshold voltage that is dictated by this V R prime B1 plus VPN. So this is the intrinsic threshold voltage which is offered by the PN junction, and the V R prime B1 is the voltage offered by the resistance between the emitter terminal and the base 1 terminal. So when you want to switch on the UJT or when you want to operate the UJT device, the voltage what we supply, basically the VEB1 supposed to be greater than this value. When this value is less than this, the UJT will not work and it will just like ideal condition. That's what it means. VPN is the barrier potential of the PN junction. Yeah, that's we know that. If you form PN junction diode, the intrinsically there will be the built-in potential. We call it as a VBI. If you have worked out the problem which I given in the very some few classes before, you will remember. So that VBI decides this basically the potential barrier or built-in potential that dictates the voltage, threshold voltage or the knee voltage or whatever. So that voltage is supposed to be higher than this combination. So then the value of emitter voltage that causes the PN junction to become forward bias is called the VP or peak point voltage, and they expressed as okay. So this is the figure. So this is the typical, the IV characteristics of the UJT. We have the current in the x-axis, that is the emitter current, what we given or we give for the emitter terminal, and correspondingly the voltage built up or voltage associated with the given current is measured in represented or represented in the y-axis. So the value of emitter voltage that causes the PN junction to become a forward bias is called the VP and is expressed as this. The value of emitter voltage that causes PN junction to forward bias is called. Basically, the voltage, basically the VP. You can just look at this region. So this is the voltage corresponding to that. It will just in the forward region, it will just enable the device to act. So that current, that voltage we call it as a peak point voltage. That peak point voltage can be estimated or calculated if you know the eta value, intrinsic standoff ratios, multiply with VBB plus VPN. That is the basic the diode voltage, and this voltage is due to the between the the base terminals. So we know how to calculate VBB also. So basically the power supply which we are given for the between the base terminals. So when VEB1 reaches the peak voltage, the PN junction becomes forward bias and IE begins. So what happens when you supply this voltage at P in such a way that it reaches VP? That means it's basically your UJT starts functioning. That means the voltage what you supplied it's switched on your UJT, and also it is in a forward bias condition. We just know this bias in the forward bias conditions, and correspondingly we can measure the current. Once the voltage reaches VEB or the voltage which is required to switch on the UJT starts, the correspondingly you will get the current. So that's we just measure here. So this looks like this in the forward bias region. So it will just goes like this. So similarly, holes are injected into the N-type bar from the P-type emitters. So during this process, the holes are injected into the N-type bar from the P-type emitter. This is obvious. The magnetic the holes will be the transfer from P regions to the N region, and this increase in a hole causes an increase in the free electrons, thus increasing the conductivity between the emitter and base one terminals. So as a result of holes or crossing or injected into the N-type bar from a P-type emitter, so what happens? So the increase in hole causes increase in the free carriers. Basically, free carriers increases happening. Supposed to be the free carriers can be basically the electrons. Thus increasing the conductivity between the emitter and the base terminal. So after turn on, UJT operates in the negative resistance region up to a certain value called the IE, shown in the IV characteristics. So once the UJT is turned on, this operates in the negative resistance region. This we have seen in the previous case also in the tunnel diodes. The diode operates in the negative resistance region. Basically, the current will start decreasing, or in this case, yeah, negative resistance. So the current starts the resistance value start decreasing. So until the point of IV, the valley point. So until this valley point, the current will sort of keep, sorry, the resistance will be keep decreasing until the valley point. After that, again starts increasing. So okay, so as in the figure, as you see, after a peak point IE, VP, and I is equal to IP, and the VE decreases as E continues to increase, thus producing the negative resistance characteristics. Beyond the valley point, V is equal to VE, that is the emitter voltage is equal to VE, that is the valley voltage, and the corresponding, and this is the corresponding current. The device is in saturation, and the VE increases very little with an increase in the resistance, with the increase in the emitter, the current. So this is the region, that region which we talk about. So after after the valley current, what we achieve. So even if you increase the voltage, what happens? There is no increase in the current. It's sort of saturated the regions, but not completely saturated current or the constant current. There is a very small increment in the current, right? So that's, or the voltage is happening. So this is the basic the characteristics of the UJT